Hello, we're going to go over our notes today on solution stoichiometry. This is the last page of your notes on page 8. You need a pencil and a calculator and page 8 of your notes. So solution stoichiometry is actually not too bad. It's actually a little easier than all the other stoichiometries because when you're given a molarity, you can think of that as a conversion factor. So right here, this 0.75 molar solution of silver nitrate, that can be used as a conversion factor. So you can literally say, okay, so for every 0.75 moles of silver nitrate, that's equivalent to 1 liter of solution. And then you can use that as a conversion factor in your dimensional analysis. Now, like with all stoichiometry, you have to start with a chemical reaction before you can actually do the stoichiometry. So let's look at this one. We have what mass of precipitate is formed when you mix 250 milliliters of 0.75 molar silver nitrate with excess sodium phosphate. So I'm going to have my silver nitrate, and I assume because it's a molar solution that it's aqueous. And if I look it up on the solubility rules, it is absolutely aqueous. And I'm mixing that with sodium phosphate. Let's assume that that's also aqueous. Okay, so then sodium goes home with phosphate, silver goes home with phosphate. So we get Ag3PO4. And then sodium goes home with nitrate, so that's NaNO3. Any solution made from an alkali metal or a nitrate is always aqueous all the time, so that one's aqueous. So the other one must be my precipitate. So I have more than enough sodium phosphate. I've only got 250 milliliters of 0.75 molar silver nitrate, and I want to know how much of the precipitate I'm going to make. So first thing I'm going to do is change that 250 milliliters to 0.25 liters. Liters is what you're going to work with this conversion factor. So you can show the work or you can just change it. It's fine to just change it. So I have 0.25 liters of solution, and that's my silver nitrate solution. So then next I'm going to use this conversion factor that I decided on earlier, right? So I want to cancel liters, so I'm going to put 1 liter of solution on the bottom and 0.75 moles of silver nitrate on the top. And since I'm already to moles, without having to go through mass or anything, I can go ahead and go straight to my mole-to-mole ratio. Now, I may have forgotten to balance this. Oh, I did. Okay, so sorry. You probably noticed. All right, so for every 3 moles of silver nitrate, I'm going to make 1 mole of silver phosphate. So my moles of silver nitrate will cancel, and my liters of solution will cancel. But I need to get to mass of the precipitate. So for every 1 mole of silver phosphate, and then I type that into my calculator. So 3 times 107.87 plus 30.97 plus 4 times 16. So 418.58 grams of silver phosphate. So moles of silver phosphate cancel. And then I just multiply across the top and divide by the bottom. and I should have 2 sig figs, because that's 2 sig figs, and that was data, and that's 2 sig figs, and that was data. So my answer should have 2 sig figs. So it should be 26 grams of silver phosphate. All right. Next thing says, when finding either molarity or volume, always divide by the one given at the end. I kind of disagree with that. I like to do it at the beginning because there will be a space at the very beginning where you can put a number if you want. So we're still going to go with the same premise that anytime you have molarity, you can use that as a conversion factor for moles equaling liters. Okay, now I'm looking for volume. Oh wait, what is the volume of this concentration of plumbic bromide that would react with 9.82 grams of calcium? So I still have to do a balanced chemical reaction. So I have calcium, which is a solid at room temp, reacting with plumbic bromide. And I assume that's an aqueous solution because they're asking me for a volume and it has a molarity. Only aqueous solutions will have molarities. All right, and so then I look at my activity series and see that calcium is above lead, so calcium will replace lead in aqueous solution. So then calcium goes home with bromide, and it is aqueous according to my solubility rules, and lead is left all cold and lonely, and that's a solid at room temp. Okay, so then I'd have to double my calcium bromide and then double my calcium, and now the thing is balanced. Now I'm starting out with 9.82 grams of calcium. I want to know how many liters of that I'm going to get, and it has a 1.75 molar concentration. Okay, so I'm going to start with the 9.82. So I have 9.82 grams of calcium. I have to go to moles. So for every 40.08 grams of calcium, that's 1 mole of calcium. Then for every 2 moles of calcium, I'm going to require 1 mole of plumbic bromide. Okay, so then I'm going to use my molarity for a conversion factor. So for every 1.75 moles of plumbic bromide, that gives me 1 liter of solution. So then I don't actually have to do anything with this empty space right here. You only have to do that when you're trying to find molarity. When you're trying to find volume, you just end with volume on top. That's all you have to do. When you're looking for molarity, it's a little bit more complicated, but it's not that bad. So then I'm going to multiply across the top and divide by the bottom. Okay. All right, and so I have 3 sig figs here and 3 sig figs here, so my answer should be 3 sig figs. So I get 0.0700 liters of plumbic bromide solution. Okay, last example. What is the molarity of ferric sulfate if 800 milliliters reacts with 0.950 grams of aluminum? All right, so we're reacting ferric sulfate And we need a molarity, so it's obviously aqueous solutions, because only aqueous solutions have molar concentrations, with aluminum. Okay, and so if I look at my activity series, I can see that aluminum will replace iron in aqueous solution. So aluminum goes home with sulfate tonight. And that's soluble. Most sulfates are soluble. And iron is left all cold and lonely. Okay, then I just have to balance my aluminums and my irons because my sulfates are already balanced. And I'm done. I'm looking for the molarity of ferric sulfate. If I have 800.0 milliliters. But I think it's easier to use liters myself, so I'm actually going to go with 0.8000 liters of that. And I have 0.950 grams of aluminum. Alright, so I want to end with a double unit because molarity is moles over liter, which means I'm going to have to start with two single units, one on top of the other. So I'm going to start with my aluminum because I want liters to be on the bottom if I'm looking for molarity. So I'm going to start with aluminum. So 0.950 grams of aluminum. And then I need to convert that to moles. So for every 1 mole of aluminum, that's 26.98 grams of aluminum. And for every 2 moles of aluminum, 1 mole of ferric sulfate is required. Now I have moles on top. In order to get to molarity, I need liters on bottom. So I'm just going to go back and put my liters in this empty space right here. So I have 0.8000 liters of solution, and that's actually the ferric sulfate solution. So I end with moles per liter. So I just do my math. Okay, and I have 3 sig figs there and 3 sig figs there. Everything else is a constant, so my answer should be in 3 sig figs. Don't mind that bell. Okay, so now you just need to work on the rest of your homework. And if you have any questions, email me or come and see me or go find an AP Chem student in room 311. Have a nice day.